Let's talk about multiplying and dividing exponential expressions that have a common base. So let's remind ourselves of how exponents work. We start with the definition. Okay. Let's go ahead and consider the number b to be a real number. And n to be some positive integer. A positive integer, that's a natural number. We can say it that way. Meaning 1, 2, 3, 4, 5, and so forth. It's a natural number, right? Then b to the power of n means that you're going to multiply b times itself n times. So this n counts how many b's are being multiplied together. Like that. So for example, if we have something like 5 to the power of 3, well, that would mean take the number 5, write it out 3 times, and multiply them together. 5 times 5 is 25, and 25 times another 5 is 125. Keep in mind that this is not commutative. You cannot just change the order because that will change the answer. 3 to the 5th power would be 5 copies of the number 3 multiplied together. 3 times 3 is 9. 9 times 3 is 27. 27 times another 3 is 81. And then this 81 times 3 is 243. So keep in mind that your order does matter. Whenever you have something like this number down here is called the base. That's why we chose the letter B here. This is called the base. And this is called the exponent, or also sometimes called the power. Okay? So here we can say 3 to the power 5. Power is a common word for that. Yeah? Now, whenever you have a base, it's supposed to be a real number. However, variables can also represent a real number. So keep in mind that variable to a power does mean the same thing. Just like 5 to the third means 5 times 5 times 5, x to the third means x times x times x. The difference is here, we actually know what these numbers are, so we can multiply them. Whereas here, well, we don't know what they are, so they can't really be multiplied. A little word on notation. If you have something in parentheses that's being raised to a power, then everything in the parentheses is going to be multiplied times itself 3 times. So here if you say minus 2 to the power 3, that's minus 2, the whole thing including the negative, times another minus 2, times another minus 2. Like this. Where negative 2 times negative 2 is positive 4. And then positive 4 times another negative 2 would give us negative 8. Just like that. But without parentheses, negative 2 to the third, like this, that would mean something different. Whenever you have something in parentheses raised to a power, then the whole thing in the parentheses, whatever's in there, is all being raised to that power. But without parentheses, an exponent only works on what's right next to it. So here, this would be 2 to the third. So you would have 2 times 2 times 2. And then you say, well, what about the negative? Oh, you throw that in at the end. Only the 2 gets raised to the third power. The negative is separate. Okay? So here that would be 2 times 2 is 4, times 2 more is 8, and then you tack on the negative at the end. Now you look at that and say, well, that's the same answer, isn't it? Well, in this case, yes, because a negative times a negative times a negative is a negative. However, if I give a different example, let's say I have negative 3 to the 4th power versus negative 3 to the 4th power. Try that. Go ahead and pause the video for a moment and give this a try and expand these out and see what you get. Once you have a result, go ahead and unpause and we'll go through it together. All right, we got it? Here, this means negative 3 times negative 3 times negative 3 times negative 3, which negative 3 times negative 3 is positive 9, times another negative 3 is negative 27, times another negative 3 is positive 81. Without the parentheses, this is simply 3 times 3 times 3 times 3, and then you tack the negative on at the end. So again, 9 times 3 is 27, and 27 times 3 is 81. And then at the end, you tack on the negative. All right, so there is our result. And keep in mind that this works for any real number, including a fraction or a decimal. So for example, we say 2/5, and we're going to raise that to the second power. Well, that means 2/5 times 2/5. If we wanted to do that to the third power instead, well, then we would do it one more time, times 2/5. If we wanted to do it to the fourth or fifth or sixth, same thing. We would just multiply it out as many times as appropriate. And then we multiply. 2 times 2 is 4, times 2 more is 8. 5 times 5 is 25, times another 5 is 125. Now, up here, I had an example where I had a variable instead of a constant. Let's look more closely at problems like this. And let's remind ourselves of what the word evaluate means. When we evaluate an expression, for a number, that's the proper way of saying, take the number and plug it in. Take the number and plug it in, then simplify. Because of course, once you plug in the number, there may be some operations which you can then take to simplify. So for example, let's say we have 5x to the second power, and then separately I'm going to do 5x to the second power. At which point you say, well, you just said the same thing. Well, no, I didn't. Well, actually, I guess I did, but here I'm writing this a different way. This is 5 times x to the second power, like this. So you have x to the second, and then you multiply that times 5. Whereas here, we're squaring the whole thing, 5 times x. Now remember, with parentheses means something different than without parentheses. As an aside, let's go ahead and look over here. 5x squared, that would mean 5 times x times x. Without parentheses, the square only affects what's next to it. But if we had 5x squared like this, that would mean all of the things in the parentheses would get multiplied. So 5x times 5x. And notice there's an extra 5 in that one. Okay? So these do mean different things. All right, so let's go ahead and take these and evaluate. We're going to go ahead and evaluate these, evaluate the expressions. And this is an example. Evaluate for x equals to 3. Okay? Again, that's the formal way of saying, okay, take that number, plug it in, and clean it up. So here that's going to be 5 times 3 squared. Okay. Remember, without parentheses, the squaring happens first. Think about the order of operations. Square happens before multiplication. So here 3 squared would be 9. And then once you have that 9, then you can multiply by 5 to get 45. On the other hand, this one would say, okay, first we're multiplying because parentheses go before exponents, order of operation. 5 times 3, quantity squared. First, we're going to multiply these together. 5 times 3 is 15. And then we can take that 15 and square it. 15 times 15 is 225. And notice that the parentheses do make a significant difference. You have a big difference between 5x squared without the parentheses. That evaluates to 45 when x is equal to 3. Whereas 5x, the whole quantity squared, is equal to 225 when you evaluate at 3. You can evaluate for more than one variable at a time. For example, we can evaluate for x equals to, let's say, 4 and y equals to negative 3. And let's say 5x y to the second power. Okay? And then over here, let's say x plus y squared. And then let's say x plus y squared. Okay? So again, these are different. All right, so let's go ahead and try this one first. This one, we're going to go ahead and substitute in wherever there's an x, we're going to substitute in a 4. So that's 5 times 4 times, now your y is going to be a negative 3, and that's getting squared. Parentheses go first, but notice that inside these parentheses there's nothing to do. They're already just a single number. Okay, so now I got to worry about my exponent. That's going to be 5 times 4 times, well, let's see here, negative 3 squared. Now this is in parentheses, right? This is just a single number. So negative 3 squared means negative 3 times negative 3, which is positive 9. And now all that's left is multiplication. So let's multiply. 5 times 4 is 20, and then that 20 times 9 is 180. So there we go. We evaluate 5xy squared, and that gives us 180. Now let's take a look at these, and we'll compare them. This first one is going to be 4 plus a negative 3. I'm going to go ahead and put the numbers as I substitute them in. I'm going to put them in parentheses to make sure that that negative stays with that 3, no matter what. So it's going to be 4 plus negative 3, the whole thing squared. Over here, this one's going to be 4 plus negative 3, and notice that here only the negative 3 is squared. So that's going to be different. Here, parentheses go first. So we don't do the square yet. Parentheses first. 4 plus a negative 3. In other words, 4 minus 3, that's the number 1. And now that we've handled the parentheses, now we move on to an exponent. 1 squared is 1. But on this one, we're going to have to do the exponent before we do any addition. Oh yeah, parentheses go first, but again, there's nothing to do inside the parentheses. Exponent is the first real operation that I need to worry about. So here, I'm going to take negative 3 and I'm going to square that. And again, as we saw up here, negative 3 times negative 3 is positive 9. So this would be 4 plus a positive 9. And then when you add 4 and 9, you get your result of 13. So notice again, with parentheses versus without parentheses means something very, very different. Here it means you square all of this stuff. Here it means you only square the y. So go ahead and give this a try. You're going to go ahead and evaluate. And we'll use x and y again. For x equal to 2, and let's say y equals to 3. Let's make this one negative. Like that. Okay, so let's use x squared plus y squared. We'll compare that to x plus y squared, like that, and also x plus y squared. All right, so try those 3. These are different. So go ahead and pause the video, evaluate these 3, and once you're done, go ahead and unpause and we'll go through them together. All right, we got it. We're going to go ahead and substitute in these values. For this first one, you're going to have negative 2 to the second power, plus you're going to have a positive 3 also to the second power. Parentheses go first, but there's nothing to actually do in the parentheses. Right? These are just already just regular numbers. So really, exponents go first, and then we do any addition. All right, so as we square this, negative 2 squared, negative 2 times negative 2, that's a positive 4. 3 squared, well, that's 3 times 3, that's the number 9. And when you add those together, 9 plus 4 will give us 13. Okay. Let's try this one. It's going to be an x, which is negative 2, plus y, which is positive 3. All of that's in parentheses, and then you square. Notice that now, you're doing the addition first. Okay, so 3 plus negative 2, or 3 minus 2, that's the number 1. And now that 1 is what's being squared, which gives you 1. Okay, so notice that squaring this whole thing is different from squaring each of these. And that's different than if you didn't have the parentheses. Let's see what happens without the parentheses. We're going to have negative 2 plus 3 squared. Notice without the parentheses, you're only squaring this number, you're only squaring the 3. So that's going to give you a negative 2 plus, that's the first thing we do, we're going to square the 3, that'll give us 9. And then when you combine those, 9 plus negative 2, in other words 9 minus 2, that'll give you 7. And there we go. These are the 3 results that we get when we evaluate our expressions using those numbers. Now, depending on our problems, we may not have values to evaluate with. We may not actually know what x and y are. We may have to do arithmetic, we may have to do algebra with these expressions as they are without ever having to substitute in any numbers. Now, that may sound complicated because, well, how do I do arithmetic if I don't know what these numbers are? Well, it turns out if we notice some nice patterns that arise when we look at how exponents work, it actually is fairly doable. So consider the following example. Let's say I was going to multiply x to the power 5 times x to the power 3. Now you look at that and you say, well, I can't do that. I don't know what x is. If I knew x was 2, okay, I could go ahead and take 2 to the 5th and then 2 to the 3rd and then multiply. If I knew x was negative 1, I could do negative 1 to the 5th, negative 1 to the 3rd, and then multiply. But if I don't know what these are, how can I do that? Well, remember what an exponent is. X to the power 5 means 5 copies of x are being multiplied together. Now you say, well, how does that help? I don't know what x is. Well, what about x to the 3rd? What is that? Well, that's 3 copies of x multiplied together. Okay, but this x to the 5th is being multiplied by this x to the 3rd. Well, this is all just one big multiplication then. Because here, the parentheses don't matter. You have 5 multiplications, and then another 3. That'll give us a total of 8 multiplications. X times 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 x. After all, it's just 8 x's multiplied together. 5 of these and 3 more of these. That'll give us x to the power of 8. But notice what we just did. We had 5 of these multiplied together, and then 3 more. That gave us 8 multiplied together. This gives us a property of exponents. Here, let's talk about multiplication of exponential expressions of a common base, meaning of the same base. Here, they both have the base of x. If b is a real number, I'm going to go ahead and use b so that it looks like the previous definition we had. B is for base. If b is a real number, and again, it doesn't have to be any constant real number. This is a variable. It still represents a real number. If b is a real number, and m and n represent integers, then if you take b to the power of n and you multiply that by b to the power of m, you're going to get b to the power of n plus m. Or in other words, to multiply two things that have the same base, you're going to add their powers. So, as further example of that, if we have x to the power of 12 times x to the power of 9, this would be x to the power of 12 plus 9. Or in other words, x to the power 21. Okay? This works for more than one base at a time. So for example, let's say we had x to the power 5 times y to the power 3. That's one expression. Now let's multiply that expression by x to the power 6 times y to the power 8. Now you say, well, yeah, but these aren't all in the same base. Here you said we have to have all the same base. Well, that's true. You can't combine them if they don't have the same base. But if they do, then those can be combined. After all, this one and this one both have the same base, which means I could combine this one with this one. X to the power 6 times x to the power 5 is x to the power 5 plus 6. Same thing with this one and this one. They both have the same base, y. So that's going to be y to the power of 3 times y to the power of 8 is y to the power of 3 plus 8. And so that's going to be x to the power 11 times y to the power 11. Same number. And if you happen to have any constants, well, that's fine. Those are handled on their own. So let's say, for example, we had 2x to the power 3, y to the power 5, and then we're going to multiply that by 3x to the power 9, y to the power 2. Whatever has the same base is going to go together. So we have x to the power 3 times x to the power 9. Okay, that's x to the power 3 plus 9. Y to the power 5 times y to the power 2 is y to the power 5 plus 2. But now you say, well, what do I do with those? Well, the same thing we always do. We multiply. After all, this is a multiplication problem. So this is the way we multiply things with a common base. This is the way we multiply these things with a common base. But these are just regular numbers. You just multiply those the traditional way. 2 times 3 is 6. And so we get 6 times x to the power 9 plus 3, that goes 12. And then y to the power 5 plus 2, well, that gives us 7. Just like that. Go ahead and give this a try. Go ahead and multiply the following expressions. Let's say we have a to the power 5, b to the power 9, times a to the power 12, b to the power 4. Okay? And then also go ahead and try 5x to the power 9, y to the power 1, times 4x to the power 6, y to the power 7. Just like that. All right, so let's go ahead and give that a try. Note here, these can go together. So that's going to be a to the power of 5 plus 12. So that'll be 17. Here, b to the power 9 plus 4. That'll be 13. And there we go. Here, these are just regular numbers, so those multiply together the way we normally multiply numbers. 5 times 4 would give us 20. X to the power 9 times x to the power 6 will be x to the power 9 plus 6. That's 15. Y to the power 1 times y to the power 7 would be y to the power 1 plus 7. Or in other words, y to the power 8. Just like that. Now, it turns out something similar will work for division. Here we see multiplication of exponential expressions. What about division? Okay. So if b is a real number and m and n are integers, then if you take b to the power of m over b to the power of n, well, let's see. You're not going to finish the thought? I will, but let's see why it should work a certain way. Let's say I have something like x to the power of 7. Okay, well that means x multiplied times itself 7 different times. Just like that. Now, let's say we divide that by x to the power of 3. Okay, well that means I'm dividing by x times x times x, just like that. Well, now when we look at it like that, we start to see that division take some of these away. After all, a number divided into itself is the number 1. X over x is really just the number 1. Same thing here. X over x is just the number 1. X over x is just the number 1. So here, our numerator is 1 times 1 times 1, which is just the number 1, times x times x times x times x, which is x to the 4th power. Our denominator is 1 times 1 times 1, which is just the number 1. And here, dividing by the number 1 doesn't change anything, so we just leave that as x to the 4th power. Oh, but look, what happened was we had 7 x's multiplied together, and then we divided out 3 of them, which left only 4 of them. 7 minus 3 gives us 4. So here, whenever you divide two things, as long as they have the same base, your exponents can subtract. So b to the power of m over b to the power of n is equal to b to the power of m minus n. Numerator exponent over the denominator's exponent. Keep in mind that that does have to be in that order. Don't switch these. It should be the power of the top minus the power of the bottom. Okay? Just like with the multiplication property that we saw just a moment ago, if you don't have all of your expressions with the same base, well, then it applies to the ones that do have the same base. So for example, if we have x to the power of 3, y to the power of 12 divided by y to the power of 7, well then here this doesn't have any expression that has a base like it. Okay, so then we just worry about these. So here this is x to the power of 3, and that doesn't change. But now these can change. We can take y to the power 12 minus 7. 12 minus 7. That'll give us x to the power 3, y to the power of 5. Just like that. If you have several expressions, well again, it's whatever works. If we have x to the power 9, y to the power 7, and we divide that by x to the power 6, y to the power, let's say just y, let's leave it like that. Well then again, that's going to be, these can go together because they have the same base. Okay, x to the power 9 minus 6. And then these also go together. Y to the power 7 minus 1. Because after all, y is like saying y to the first power. So even though it's not written, y by itself has a power of 1. So putting these together will give us x to the power of 9 minus 6 will give us x to the power of 3. And here y to the power 7 minus 1 is y to the power of 6. And if you have any constants, well then those get treated the way they normally get treated. For example, if I have 81 x to the 5th power y to the 9th over 3 x to the 2nd y to the 3rd, well then here y to the 9th over y to the 3rd, that's y to the 9 minus 3. X to the power 5 over x to the power 2, that's x to the power 5 minus 2. And here, these are just regular numbers. You just divide them. You take 81 divided by 3. And here we can simplify. 81 divided by 3 is 27. X to the power 5 minus 2, that's the same as saying x to the power of 3. And then y to the power of 9 minus 3, well, that's power 6. And there's our result. Note that you can combine these properties. For example, let's say we're going to multiply x to the power 9 times x to the power 7 over x to the power, let's say, 11. Here, you have an instance of multiplication and an instance of division. Well, that's fine. You can combine these. Here, let's go ahead and multiply these together. This would give us x to the power of, that's 9 plus 7, because when you multiply, the powers get added, which is x to the power 16, 9 plus 7. But then you're going to divide that by x to the power of 11. And when you divide, the powers get subtracted. So that's x to the power 16 minus 11. Or in other words, it's x to the power of 5. And there we go. 9 plus 7 makes 16. And then you subtract 11 to give us 5 as our power. So go ahead and give this a try. You're going to simplify. We say 24x to the power of 8, y to the power of 7 over 6x to the power of 5 y, like that. And you're going to simplify x to the power 9, y to the power 6, times x to the power 5, y to the power 4, over x to the power 11, y to the power 3. All right, so go ahead and give this a try. Go ahead and pause the video, and once you are done, go ahead and unpause, and we'll confirm these together. All right, so this first one, we're going to do just regular division. It's going to be 24 over 6. Here, we're going to subtract away their powers because they have a common base. They both have a base of x. So that's x to the power 8 minus 5. And then here, that's going to be y to the power 7 minus 1. Because after all, y by itself is like saying y to the first power. So that's going to give us the number 4. 24 divided by 6 is 4. X to the power 8 minus 5, that's x to the power 3. And then here, y to the power 7 minus 1, well, that's power 6. And there's our result. This one, notice we can go ahead and do the top. And when you multiply these expressions, you're going to add their powers together. So this is going to give us x to the power 9 plus 5. 9 plus 5. And this is going to give us y to the power 6 plus 4, which is x to the power, well, let's see, 9 plus 5 is 14. And y to the power 6 plus 4 will give us 10. But now, you're going to divide that by x to the power 11, y to the power of 3. So, when you multiply, the powers get added, but when you divide, the powers subtract. So this will give us x to the power, we have 14 minus 11. And here we have y to the power 10 minus 3. Which will give us, well, let's see, 14 minus 11, that's x to the power 3. And then 10 minus 3, that'll give us y to the power 7. And there's our result. All right, so it looks like that is it for now. If anybody has any questions, comments, or problems, please make a note of those. Reach out, and I hope everyone has a nice day.